useful for later. So the question is asking to find this line integral. Oh, this is a line integral, by the way. How do I know what this is? This is basically the dot product of x plus yz, 2x and xyz dr. Right? And so it's a line integral. And I do recommend checking if the, which one is f here? This is the vector field. I do recommend checking whether or not the vector field is conservative. It's helpful, basically. If it's conservative, the line integral is much easier to do. I just have to plug in, find the potential, scalar potential, and plug in the endpoints, right? So let's do that first, see if it's conservative or not. In here, function, the f is defined everywhere. It doesn't have any hole in the domain. Now, so let's do the, basically the gradient of f, I'm sorry, curl of f. And curl of f is ijk, partial respect to x, partial respect to y, partial respect to z, and x plus yz, 2x, xyz. And in here you get xz minus 0 times I, and then you get, and as soon as I did that, I realized, oh, this is not going to be conservative because I'm not getting a 0 vector. So the f is not conservative. So I can't use the conservative, basically conservative fundamental theorem of conservative fields. Whatever that is, not equal to 0 vector, not conservative. So my next thing is that it just seems that I have to do my work and find each piece and find them separately. So how do we do this? There are two pieces. One piece goes from here to here. I call it R1 of t. The other piece goes from here to here. I call it R2 of t. Right? So what is R1 of t? R1 of t connects the 1, 0, and 1 to 2, 3, and 1. My recommendation, because beginning point and end point matters and you want to have a nice t, is to take beginning point, start point, and find the vector from beginning to end. This is beginning, this is end. And so vector from beginning to end is what? Is v equal to 2 minus 1 is 1, 3 minus 0, and 0. So my recommendation is to find R1 of t to be the beginning point plus t times that vector. And so this basically becomes 1 plus t, 3t, and 1. Do the same thing for the second one, for R2 of t. R2 of t, was that 1, Parveen? And so again, start point and end point. Find the This one was V1, this one is V2. 2 minus 2, 0. 5 minus 3, 2. And 1. And then write R2 of t to be the beginning point. Oh, 2, 3, and 1. T times 0, 2, and 1. And that is 2 plus 2 and 3 plus 2t plus 1 and 1 plus t. I messed up it multiple times, right? Now I have R1 and R2. Meanwhile, find R1 prime, which is going to be basically V, and R2 prime, which again is going to be T. For lines, it's going to be that V, basically. Now, the beauty of this parameterization is that T is between 0 and 1, starting at 0 and ending at 1. Now what I need to do is basically plug in R1 into my vector field, and then dot it with R prime, and then integrate from 0 to 1. So I will have, let me write down the vector field right here. F of x and y and z is x plus yz, 2x, and xyz. And so basically, the integral over c, the integral over c of f dr breaks down into two integral from 0 to 1. The first one, plug in this into here, and I get x, which is 1 plus t, plus yz, which is 3t. And then 2 times 2 plus 2t, and xyz, which is going to be 3t plus 3t squared. And I dot that with 1, 3, and 0, and take the integral of that. And over here also plug in R2 of t, which is that. So this was basically C1, and this was C2. You break it down into that. So this entire thing is just the C1, and that one is over C2.
Professor?
Yes.
How do we know how do we know that the bounds are from 0 to 1?
Oh, the format that I used to parameterize is just basically when you plug in 0, you see that you get the start point. When you plug in 1, you get the end point.
Oh, okay, right.
So that's the beauty of this one. And when I say that the other parameterization for plane, if you have, because these are, you technically don't get the entire plane, right? You just get piece of a plane, and usually you get a rectangular piece of a plane, or
right.
that's the one that we emphasize this semester. Usually we get more than that on regular semesters, but this semester we just, the entire emphasis was just the rectangular or parallelogram shape. And so that other type that I told you about, parameterization of the plane, that one also gives you t and s between 0 and 1. That's again another beauty of it, basically. And so now I'm going to basically over here plug in that R again. This is long, but we're going to get there. And so you will have 3 plus 2t times 1 plus t. And then you have 2x, which is 4. And then xyz, which is 2 times 3 plus 2t and 1 plus t. 2 times 3 plus 2t and 1 plus t. And then dotted with the r prime. I needed more piece of paper. I should have not done this. So the integration becomes, so f dot dr, which was f dot dr over the first piece plus f dot dr over the second piece. For the first piece over here, I will have the integral from 0 to 1, 1 plus t plus 3t times 1. So it's 1 plus 4t. Then 2 plus 2t times 3, that's 6 plus 6t dt. And over here, I will have 0 times that, which is going to be 0. Then I will have 4 times 2, which is 8, plus 1 times multiplication of all of them, which is going to be 2 times 3 plus 2t times 1 plus t dt. And that gives me the answer. Was that okay?
Yes, that made a lot of sense.
Okay, good. So what's the next question?
I think question 1 from this fundamental theorems. I think it's pretty similar to the piecewise, if I'm not mistaken.
Okay, question 1 from the fundamental theorems. Yeah, right there.
Yeah.
Okay, so let me write down the question itself. The question is saying the scalar function f of y, x and y and z. See, output is just 1. And then there are paths that start from 0, 0, 0 to 1, 0, 0. And then it goes to 1, 1, 0. Oh, how many paths? One is this connection, which is C1. The other one is C2, then it's C3. Oh, no. You can see this part, right? Sorry. Sometimes I forget. So I have that. And then this is the first one. Then, and then we're asking for the line segments that goes from 0, 0, 0 to 1, 1, 0, then to 1, 1, 1. So this is a bit different. This is still C3. 0, 0, 1 to 1, 1, 0. This is a different one though. This is C4. Okay, so now here is, let me close this. Okay, so here again, my feeling is that this actually may be one of those occasions that, wait, what was the question again? Oh yeah, it's just integrate. So no, this one is just integrate, and it's the scalar line integral. The other one was the basically the vector line integral. So the difference is the scalar line integral versus the, maybe the question is misplaced in that area basically. So here, for the first one, I have 3 paths. So let's do C1, C2, and C3. And for C1, starting point is this, end point is that. So I can write R1 of t equal to 0, 0, 0 plus t, the vector that goes from here to here, which is 1, 0, 0. So R1 of t is t, 0, 0. Then R2 of t is equal to, in here, going from this point to that point. So it starts from 1, 0, 0, then t times, and the difference is 0, 1, 0. 0, 1, 0. So this is going to be 1, t, and 0. And then R3, again, starts at here and ends there.
Professor?
Yes.
Is there like a specific way to tell if it's supposed to be a scalar line integral or a vector line integral?
Oh, it's telling you, see, this is a scalar function, right? Do you see that one?
Yes.
How many components is coming out, the output?
3?
No, components as in, do you have a vector?
Oh, no.
There's no vector, it's just the, there's no components in there, it's just that it's a scalar.
Oh, okay, okay.
So that was the thing, and I think I misplaced one of the questions in the in that area.
Right.
Unless I didn't read the next question well, but I think I misplaced this one. It's supposed to be in the other area, and it showed up in here, so I may fix it later. So now this t times 0, 0, 1. And that is going to be 1, 1, and t. Now you have these. R1 prime of t is going to be 1, 0, 0. R2 prime of t is going to be 0, 1, 0. And R3 prime of t is 0, 0, 1.
Shouldn't for R3 be negative 2?
Negative 2, where is the
Oh, wait, no, that's my bad. Yeah, you're right. Sorry.
No problem. So here I find the magnitude, and that is 1 because it's square root of 1 plus 1 plus 0 plus 0. And R2 magnitude is also 1, and R3 magnitude and still 1. Now, what is the, so what we do with the scalar line integral, it's f ds and over the c, but this is going to break down into f ds over c1 plus f ds over c2 plus f ds over c3. And that is this one. Again, all these parameterization were nice because we knew t is going to be between 0 and 1. So the first one is just going to be plug in into the f. Let me write down f again. Plugging into the f, R1 of t. Where's R1? Right there. So plugging in t for x and 0 for the other one, I get t2, and then multiply by the magnitude here, which is 1, dt, 0 to 1, Then you go integral from 0 to 1, and f ds, plug in f, plug in r2. So you get 1 for x and t for y. So it's 1 plus t and 0 for z. And then multiply by that magnitude, 1 dt plus 0 to 1. And then in here you get for x I plug in 1, for y I plug in 1, for z plug in, so it's 2 minus t, multiply by that, 1 dt, and then you compute it, which would be t to the third over 3, 0 to 1, plus t plus t squared divided by 2, 0 to 1, plus 2t minus t squared divided by 2, 0 to 1. 1/3 plus 1 plus 1/2 plus 2 minus 1/2. And that is 3 plus 1/3, which is 10/3. So that's 10/3. That was part A, right? Funky part of part B is this. Part B, function hasn't changed. Function hasn't changed. And this piece is going to be the same for part B. The only thing that I have to find is the integral from 0, 0, 0 to 1, 1, and 0. So for part B, this is what I'm going to do. C4 is going to be 0, 0, 0 plus t times 1, 1, 0. That's R4 of t is going to be t0. And so R4 prime of t is 1, 1, 0. Now, what was the function? Function is that. And I have to find the integral over C4 f. Oh, I keep putting dot in there. And that, oh, one more thing. I have to find the magnitude R prime. And that is square root of 1 plus 1, square root of 2. So this time around, plug in that into here. I get t squared plus t, 0 to 1, 0, t squared plus t, times square root of 2, dt. So I get square root of 2, 0, 1. So 1/3 plus 1/2 is 5/6. 5/6 of square root of 2. And then to find the integral over, basically here was C4 and C3. I have to add that C3 that we found right there. Oops, sorry. So this one I found was 5/6 of square root of 2, and the other one is, we computed it down there to be 2 plus minus 1/2. And that would be the final answer. I think.
Are we adding it with C3 because it says that it goes from 110 to 111?
Yes, so see, it tells you for part 2, it tells you to add this piece and this piece.
Right.
So there are 2 pieces. This piece was the same as we did over here. C3 was the same. We've already computed that one. But C4 we haven't computed because this is different. Even though, see, there is a C1 plus C2, and then the end point of, beginning point of C1 is here, end point of C2 is there. But they're not going to give you the same answer, basically.
Okay.
Because they're different paths. It's what you're doing here. And again, beginning and end points for this type of, for scalar integral doesn't count, because scalar integral is finding the, let's say, weight of a wire, height of a wall, that sort of things. It doesn't matter where you start to integrate this end or that end. But with what is the other one? With the vector line integral, it matters which end you start.
Okay.
So the direction matters for the vector line integral, but it doesn't for the scalar line integral, because it gives you heights, or gives you that sort of things, basically, weight or something like that. It uses density over a curve, basically.
Right. That makes a lot more sense now.
Better?
Yes, a lot better.
So let's see, why is that question in the wrong place? That's my next question. It's not a question that you can answer. Like, I don't know why this happened. That's funny though. Yeah, that just got out of the place and was added to that piece instead of being in the right place. And sometimes happens. It should have been right here with this one. You found it though. Good job. It's just, I'm gonna check it out. Okay, tell me, what are the questions?
So I was looking through the questions just now, and so for question 4 in the same section.
The one that is up right now?
Mm-hmm.
Okay.
Yeah. I think it's like, oh no, sorry, not this one. I think the lower, like the fundamental theorem.
Okay, this one?
Yes.
Okay. Cool.
Yeah, I'm confused about like the first octant thing. Like, does that affect how we solve the question?
What is this? And so calculate the work done by the vector that in moving a particle from this point to that point along a path which stays within the first octant. So do you know why this is happening? Because so look at the, do you remember when I talked about conservative fields, there were two things that you had to check for conservative fields. Let me write this down first, because I have to have it right here. So the two things were, one was the curl, and the other one was the path goes from 1, 2, 10, 3. So the story with the conservative fields was that you have to have, if a field is, if basically you're over a domain that the vector field has curl equal to 0, so nice domain though. And so if the curl of F is 0 vector and the domain is simply connected, domain is nice, right? Then the field is conservative, and the field is conservative on that domain, and then it would be path independent. So you can plug in, you can find a scalar potential and then go through whichever of the paths that you want to. And so as soon as it tells me first octant, and I'm looking at this path, and looking at the vector field, do you see y in the bottom? That's a problem. That's a cause of a problem. Y in the bottom, z in the bottom is a cause of a problem. Anything that makes the underscore root negative is a cause of a problem. So it tells me the domain. It tells me don't just don't have two pieces of a domain, because I can also be in the 8 octant, and this function still would work, right? But they're like two pieces and they're not connected to each other. So that causes a problem with the conservative fields, basically. So this part of the first octant is so the domain is nice. Okay, so that's the first thing first. So, and I keep saying this, and it feels like I have a feeling that this thing is basically conservative. This was in the other section, right? So I'm hoping it's conservative, because otherwise it would be a mess. Let's hope and let's try to find. So domain by the question is nice. All I need to check is that curl. So let's check the curl of F. IJK, partial X, partial Y, partial respect to Z. And then 1 negative Z over Y to power 1/2, negative Y over Z to power 1/2. And so the first one round is going to be for I. What I get is the partial respect to Y of that. That is negative 1/2 of YZ to power negative 1/2. Then partial of this with respect to Z, and that would be negative 1/2. Oh, I did something very wrong, didn't I? Didn't do the derivative of inside. And so negative 1/2 derivative of inside is going to be derivative was with respect to y, so I get 1 over z. And then subtracting on the partial respect to z of z over y, and that is minus y over minus 1/2 y over z to power negative 1/2 z over y. Z over y to the power negative 1/2 times derivative of inside with respect to z, which is 1 over y. Let's see if this cleans up and then do the rest. And so if I clean this up, I get z over y to power 1/2 divided by z. So this part is negative 1/2 z to power 1/2 y to power 1/2 times 1 over z minus plus 1/2 y to power 1/2 z to power 1/2 1 over y. Oh, these two are the same thing. So this ends up to be 0. So this entire thing ends up to be equal to 0. So we're on the right path. That was the first one. If it wasn't 0, we would just stop. It's not conservative. Now let's see if it is conservative or not. And so the next part is j, and I'm taking partial of that respect to x, which is 0, partial of 1 respect to, so that's a 0, plus k, and for k, this partial again is 0, this partial is 0, 0. Oh, this is a conservative field. Our life is so much easier now. Now let's do a compute the answer using the conservative field. So what is the story of conservative fields? To be able to compute f dot dr for a conservative field, find, oh, this should be lowercase, find scalar potential first. Let's go back to f. F is that. And so how do I find the scalar potential? To find the scalar potential, integrate the first component with respect to x, integrate the second component with respect to y, integrate the third component with respect to z. And then take the common pieces and then check to see if the uncommon pieces are part of the constants. That's the rule. And common piece here, the integral of 1 respect to x is just x. And the constant is going to be in terms of the other two. So C1 of y and z. This one, y is the variable. So it's basically break it down into negative z to power 1/2 and y to power 1/2. And so y to power 1/2, it's so negative z to power 1/2, and y to power 1/2 becomes y, negative 1/2 becomes y to power 1/2 times 2. And the constant should be in terms of the other two variable, x and z. And the third one, again, with respect to z, but it's negative y over z, and it turns out to be negative 2z to power 1/2, y to power 1/2, plus c3, the other two variable, which is x and y. Now, what are common parts? That's a common part. Write that one once. So potential is the common part. And then make sure that the common part where it doesn't show is here, right? But the common part is a function of y and z. And therefore that's okay. It could be part of this. We just missed it. So that's fine. Now check the uncommon part. Uncommon part is x. Can x be part of this? Yes, it could be a function of x and z, could be part of a function of x and z, and it could be part of this constant. So that one is okay too. And then you may have a constant going on in there. But it doesn't matter because I just need one, so I can assume that the actual constant is 0. And so I just need one of the potentials. And potentials are all different, and potential functions for f are all different in one constant. Now that I have this thing, all you need to do to find this integral is to plug in, negative 2z to power 1/2, y to the power 1/2 plus x, and plug in the endpoints. What were the endpoints? Endpoints were 1, 1, 1 and 10, 3, 3. So it goes 1, 1, 1 and 10, 3, and 3. And then plug it in. This is for x, this is for y, this is for z. Plug in 10 and 3 and 3, negative 2, 3 to the power 1/2, 3 to the power 1/2 plus 10, minus, plug in 1, 1, 1, and you get negative 2 plus 1. And so this is going to be negative 2, 3, negative 6 plus 10, minus, minus 1, 4 plus 1 equal to 5. Did that make sense?
Yes, it did.
Was that easier than basically, because as soon as it tells you that any path, you're starting to think, am I able to do that? Does it make sense to use any path? When does it make sense to use any path? When the field, the vector field is path independent. When is it path independent? When it's conservative, basically. And so that's why I checked the curl. That's why I found the potential. And that's why I used the potential to find the line integral. Because I couldn't have done it any other way. It would have not made sense, basically. That was a problem. Because if it's path independent, if the question is suggesting that it's path independent, it has to be conservative. And that's a part, basically. I was going to make one more comment about this. Let me think. So I said that, and I said this, and Tarvin, can you remember what comments I was going to make?
I'm not too sure.
I don't remember neither. Okay, it doesn't help. It does not help at all. So that's the, yeah, I did the, what's that? Oh yeah, this is the comment I wanted to make. Look at this part. When you're doing f.dr, right? And you're finding a potential and then you're plugging in, this looks like a Calc 1 problem. In Calc 1, we used to do this. We would find antiderivative. In a sense, this is an antiderivative because gradient of this is equal to f. So in a sense, this is an antiderivative of f, and you're plugging in, except Calc 1 was just x. In here, you plug in x, y, z.
Right.
Those are the fun parts. That's why we call some of these things fundamental theorem of, and this is fundamental theorem of conservative fields. The other one is, again, they're called fundamental theorem of something, basically. They're fundamental theorems of Calc 3. Okay.
Thank you so much.
No problem. Any other questions?
I think I'm good for now. I'll probably just practice more of these questions.
Am I allowed to post this video?
Yes.
Okay, so I'm going to post this video to pause recording. No, stop recording. There we go.